Okay, I'm going to talk to you a bit about our project to build what we think will be the world's largest telescope. I'll give you a little bit overview of the science and then talk some about the interesting technology and then talk about, where we might go from here. In particular, I'm going to cover sort of the overview of the project, what it's about, why we're doing it, give you a little historical context about big telescopes and the evolution of large telescopes on the Earth. Then we'll spend a lot of the time talking about what we want to do scientifically, the science goals, opening new discovery space. That'll probably be the fun part of the talk, or the most fun. Then we'll spend some time talking about how you make giant mirrors, how you make mirrors that are 25 meters in diameter, 25 feet, 8.5 meters, and how we combine them together to make a single 25-meter diameter telescope. Talk a bit about adaptive optics, how we defeat the blurring caused by the turbulence in the atmosphere. We've all seen that when you take your telescope out on a kind of a night where there's a lot of turbulence, a lot of temperature profile, the images shimmer. That's no good. There's a way now with enough technology you can defeat that and produce images from the ground that are just as sharp as you get from space and even sharper. Then we'll talk a little bit about our site in Chile. It's a wonderful place. It's about as good as Mount Wilson. If you could turn off all the lights down below, it's actually a great place to be, and you'll see some shots of the site and why we want to put our telescope about 8,000 miles away. But just to give you an overview of what this is about, our goal is to build the next generation giant telescope to do basic research in cosmology and astrophysics, but mostly to discover new things, to learn about things we don't know, learn what we think we know and actually turns out to be wrong. We're going to do this by building a giant aperture comprised of 7 of the world's largest telescope mirrors, put together on a single mount and combined coherently to act as a single telescope. We'll then build this on top of an extremely compact telescope mount that's kind of related to the Dobsonian telescopes that you use, that is an altitude azimuth mount. We'll then put a dome around it because you have to protect it from the weather and the sunlight during the day, but the dome is very open, allows lots of airflow, so we make sure we get excellent image quality. And then we'll put it on a mountain in Chile where, unlike in the animation, there's not clouds blowing over all the time, but it's in fact, the artists just love clouds. You can't get artists to make a picture without clouds because they make color, but it's a site that has fantastic weather, dark skies, wonderfully sharp images, and then we will equip it with a state-of-the-art adaptive optics, high-power lasers, so we can take images that are 10 times sharper than those taken by the Hubble Space Telescope, pretty much anywhere in the sky, anytime we want. So that's the goal. It's a pretty ambitious goal, and it's not something you can do simply. It takes a lot of institutions, a lot of talent, a lot of money, I'm sorry to say, and so it takes almost a global enterprise to build something on this scale. So we brought together a number of the world's leading institutions in astronomy, going back to the Carnegie Institution that built the Mount Wilson telescopes. And then we bring in Harvard. They built the first telescopes in the United States. The University of Chicago that built the Great Yerkes refractor. University of Texas that built the McDonald Observatory, University of Arizona that built all kinds of telescopes in southern Arizona, Smithsonian Institution, which now runs the multiple mirror telescope in Tucson, as well as a newcomer in astronomy, the Texas A&M University. It's a real physics powerhouse, and now they're getting into astronomy. And then across the ocean, we're partnering with a number of institutions in Australia. They built the Great Melbourne Telescope, which at the time was the largest telescope in the world. Turns out Australia is not a great location for doing astronomy itself, but there's a lot of great astronomers there, a lot of great talent. And then a newcomer to astronomy, the Korean Astronomy and Space Science Institute. It's a country that's got a lot of technological prowess. It's the home of Samsung, Hyundai. They're very interested in astronomy and space physics, and they've joined us then to make that leap to the next generation of big telescopes. So it's a big group spread out around the world, but it's what we need to bring together the talent, the resources, the technology to build something on this scale. We're going to talk a bit about what we want to do with a giant telescope, but the most important thing is we want to discover new things. You all know this, that the history of astronomy is the history of discovery. Starts with Galileo. It actually even predates Galileo, but every time someone builds a bigger telescope or accesses a different part of the electromagnetic spectrum, whether it means building radio dishes or going above the Earth's atmosphere to observe in the ultraviolet or the X-rays, we learn things that we never anticipated, and often we find out things we thought we knew were true are not the case. So we want to build a big telescope primarily to learn new things. And this goes back right to the very beginning of astronomy, which goes back to pretty much when there were people who actually looked up at the night sky. So a long time ago, there were many, many astronomers. And it turns out your eye is actually a pretty sophisticated optical instrument. You all know that when you go out on a dark side, out in the desert or out in the mountains. Your eye can see a lot of stuff. The collecting area of your eye on a dark night is fairly small. It's about 0.2 of a square centimeter. But you have the sensitivity to detect 50 photons. That is, your eye exposes for about 1/5 of a second. And if you're fully dark adapted and look at the faintest stars you can see, that amount of flux is about 50 photons per 1/5 of a second that your eye integrates. That's pretty amazing. I mean, 50 photons is not a lot of light. And there's a claim that some people who have particularly good vision in a closed laboratory situation can detect individual photons with their eye, which really is quite amazing. The angular resolution of your eye is set by the number of wavelengths across the aperture. That's the same for any optical system. You all know you make a bigger telescope, and barring the atmosphere, you can see finer details, and that's set by how many waves span the aperture of your optical system. Your eye spans about 20,000 wavelengths, and that turns into an angular resolution of about 1 arc minute, 1/60th of a degree, which means if your eyes are really, really good, you could just barely resolve the disk of Jupiter. I can't do it. Maybe some people can. Actually, it's the rods and cones in your eye that provide the real limit, but your eye optically has the capability of resolving Jupiter. Now, as I said, lots of astronomy throughout history has been done with the naked eye, and it's worth remembering that even when we build these great observatories, the most fundamental discovery in astronomy, perhaps the most fundamental discovery in all of science, was based on naked eye observations. So in some sense, the world's greatest observatory, the first observatory, was Tycho's Uraniborg on his island there off of Denmark, where, as you know, he measured the positions of Mars, Jupiter, Saturn, fixed stars, night after night, year after year, that then Kepler used to derive the orbits of the planets and show that, in fact, that it is the sun, not the Earth, that is at the center of the universe, and that the planets go around on elliptical orbits. So lots of astronomy done with the naked eye, but in fact, the thing that really opened it up was Galileo, who didn't actually invent the telescope, but he was the first person that we know, or at least the first person who extensively turned the telescope up to the heavens. And we all know the story. He saw craters on the moon, phases of Venus, moons of Jupiter, unfortunately sunspots, which is not a good idea. We all know, don't look at the sun through a telescope. It did Galileo some real damage. His early telescope could not quite resolve the rings of Saturn. That came for the next person, for Christian Huygens. But Galileo changed the world by simply looking through a telescope and pointing it heavenwards. The collecting area of his telescope is about 10 square centimeters. That's a big gain over the human eye, about 50 times the collecting area. And instead of reaching to about 6 magnitude that most of us can see, he could go to 11th magnitude, a factor of 100 difference in flux. And he could resolve things on a scale 10 times better than what your naked eye does. That's what allowed him to see the phases of Venus, the moons of Jupiter, and so on. So this small telescope changed the way all of humanity looks at the world, looks at science. Since Galileo's time, the size of telescopes has grown exponentially. And what we mean by exponential, that means it grows by a fixed fraction every year. And the rule of thumb is that the size of the biggest telescope on the planet doubles roughly every 40 years. So what I'm plotting here is the size of large telescopes versus time from 1609 to what we're projecting out to 2020. And lots of your favorite telescopes are listed here. This is the famous telescope built by Hooke, where he started to see a structure in the Milky Way. Herschel, who discovered binary stars and the spiral nebulae. Ross, who measured the structure of spiral galaxies before they were known to be galaxies. This is the 100-inch at Mount Wilson, the 200-inch, then all the 4-meter telescopes, Keck, and so on. The point of this is to show that technology drives the development of telescopes. It drives much of the development of astronomy, and we're due for the next generation giant telescope. The first 10-meter telescope went online in 1990. You add 30 years to that, you get to 2020. That's the time when we think our telescope will be done. And it pretty much follows an extrapolation of history. This is where the GMT will be in 2020. It makes sense. It's interesting, though, to look at this in context of other ambitions. About 10 years ago, the Europeans thought they could just jump history and build a 100-meter telescope in one go. So looking at this curve, their telescope was going to be up here. Kind of hard to believe based on 400 years of technology that they could make one giant jump. Well, they've changed their plans. That didn't work out too well. That was what you call a bridge too far. Now, the way we're going to do this with the GMT is we can't build a single 25-meter mirror. There's a number of reasons for that, one of which has to do with the basic structure of the material. It's hard to get glass to cool uniformly on that scale. It tends to build up stresses. But even if you could, imagine you could build an 84-foot diameter mirror. What do you do with it? How do you get it to the top of a mountain? How do you get it to a boat anywhere? There's nothing you can do. There was discussion in the 80s of perhaps actually building mirrors on the mountaintops where the telescope was going to go. Well, that turns out to be pretty impractical. So we think that the largest individual mirror that you can actually deal with, you can actually manage, is about 9 meters in diameter. And to be conservative, we back that down a little bit to about 8.5 meters. So we're going to use 7 of the world's largest mirrors and put them together, but not to make 7 telescopes all looking in the same direction, but to make one telescope by taking the optical surface and kind of cutting it up with a cookie cutter. So we have 7 mirrors, 6 of which are just off-axis sections of a parent mirror, and 1 of which is just kind of the cookie cutter out of the center. We tip up the ones on the outside just to make it easier to put the whole thing together. And together then it has a collecting area of about 380 square meters. Remember, we went back to your eye is 0.2 of a square centimeter. We're now at 20 million times the collecting area of the eye. That's a lot. That's a lot of collecting area. It's about 10 times the collecting area of the biggest telescopes on the Earth today. The angular resolution, remember we talked about how your eye has about 20,000 wavelengths across. This telescope has 20 million wavelengths across the aperture. So it's a factor of 10 better than the Hubble Space Telescope. It's millions of times better than the angular resolution of your eye. You're probably all familiar with your telescope basic specifications, the focal ratio. If you've got an f8 telescope, it's kind of long. If you've got f6, it's kind of short. We're building this telescope with a primary focal ratio of f0.7. It's faster than f1, and that makes it much more compact, makes it less expensive, makes it stiffer, but makes it really hard to do optically. To grind that curvature in that's faster than f1, that's really hard. But that's what we have to do just to make the thing affordable. So this is a neat graphic I like that shows the 7 mirrors, shows a person standing here to give you some idea of the scale. Really, we're talking about an enormous size collecting area. Now let's talk for a few minutes about the science that we want to do. This is based on our current sort of expectation and understanding. Remember, the real goal is to discover new things and find out what, our betters and our elders tell us is right that turns out to be wrong. But when we think about the science, you can organize it lots of ways, but I like to start here and look out in the solar neighborhood, look out through the Milky Way, nearby galaxies, and then all the way back to the beginning of time. So first thing we want to do is we want to understand planets around other stars, solar systems that are different than our own, and in particular, we'd like to find out, are there planets out there that are habitable, that could support life? Planets that have rocky structure, water in a temperature range where it's liquid, where it's neither all solid ice or steam, and planets that have basically stable orbits like the Earth, proper temperatures, proper sizes that might actually be interesting places for people to live. If we then look out on a larger scale and want to understand how do those planets come into being, we want to understand the formation of stars because that's tied into the formation of planets. That means sort of surveying the Milky Way for a wide range of star-forming environments. We then want to look a little further out on larger scales to understand the formation of the chemical elements, how we went from a universe that was just hydrogen and helium and a tiny, tiny amount of lithium, beryllium, to a universe that's rich in chemistry, full of iron and nitrogen and carbon and oxygen and all the usual things that we're familiar with. Then on larger scales, we want to survey the properties of galaxies, and in particular, their central black holes, and we'll talk about that for a minute. And then looking on larger cosmological scales, measuring the properties of dark matter and dark energy, and then ultimately looking all the way back to when the universe was maybe 100 million years old, and we can see the first stars in the first galaxies as they came to be born. So that's how our science plan is organized. Let's talk a bit about planets, and unfortunately these guys are a little stretched, but that's okay, you'll get the idea. When I was a graduate student, we didn't know of any planets outside the solar system, and we really never expected to detect any. And if we did, we didn't think they would be very interesting. We thought the solar system was pretty archetypal. And from an astronomer's point of view, the solar system, while beautiful, is kind of dull. There's one big planet, which is Jupiter, and it goes around in a circle. And interior to Jupiter, there's some rocks, which we call Earth, Venus, Mercury, the Moon. And Jupiter protects all of us, which is very nice. By being this big planet in a circular orbit, it deflects comets and asteroids and other things that don't get into the inner solar system, at least not very often. And then out beyond Jupiter, there's a couple of snowballs we call Uranus and Neptune, and then a few more rocks like Pluto that are relatively insignificant from a dynamical point of view. So it came as a big shock when people started searching for planetary systems and they found ones that are completely different than our own. The first extrasolar planets that were found had the masses of Jupiter, in some cases 2, 3, 4 times the mass of Jupiter, but orbits like Mercury. So they would be Jupiter-mass planets in close to their stars. They would go around in just a few weeks, in some cases even a few days, and they're literally just boiling away. They're roasting from the light of their central suns. Massive planets in close that shouldn't be there, that are basically evaporating and boiling away. Some of them are on highly elliptical orbits, almost like comets, so they come in really close to their star, they heat up, and then they go out, and they cool off, and then they come back in. But solar systems that are very different than our own. Then people searched for a little longer so they could measure longer periods, and they detected massive Jupiter-like planets but are way out and are frozen, essentially ice worlds in which nothing, as far as we know, ever happens. They're just giant balls of ice. Lots of other exotic kinds of planets have been found lately. My favorite are the so-called water worlds. They are planets that are 10 times, maybe 100 times more massive than the Earth, and yet from their densities we deduce that they are essentially nothing but bottomless oceans. That is, they're massive planets, but have a density of water. They have an atmosphere that's probably mostly steam, and then it's just water all the way down. That would be an interesting place to live. Most interesting, though, I think in the past several years, primarily due to the Kepler satellite, we've now found a number of what they call super-Earths, which are rocky planets with diameters of 2 or 3 times that of the Earth, and the mass goes like the cube of the diameter, so you can see pretty quickly they get up to be about 10, 20, 30 times the mass of the Earth. They tend to be in Earth-like orbits. They are probably Earth analogs, but simply on more massive scales. And we don't quite yet have the sensitivity to see individual Earth analogs, but we're getting there pretty quickly. So the bottom line is that what we understand now about planetary systems is that they're vastly more diverse than we thought based on the solar system alone. Lots of interesting things going on and lots of important questions. The problem is it's really hard to actually see them. So if we went to Alpha Centauri and looked back towards our solar system, it would be very hard to see Jupiter, almost impossible to see the Earth. And that is because as we go outside at night and you look at the planets, you're seeing sunlight reflected off of them. Jupiter only reflects about 1 part in 100 million of the sun's light. The Earth reflects about 1 part in a billion, and from the distance of even the nearest star, their separation on the sky is typically about 1 arc second or less. Remember, an arc second is a 60th of an arc minute, which is the 60th of a degree, and so that's a very, very small angle. So the problem is you have a faint star very, very close to a faint planet very close to a very bright star, and it's extremely difficult to separate the two, which is why you don't see lots of pictures of planets around other stars. It's very hard to do. One way to address that then is to build a really big telescope that has so many wavelengths of light across the aperture that you can achieve that high angular resolution and the high contrast you need, and that's what we're aiming to do. So here's an example. We can look out in the infrared where the planets, rather than reflecting light from their central star, actually radiate their own light because they're still hot. You know, if you look out at, say, at 10, 20, 30 microns, the planets, rather than being 100 million times fainter than the stars, are only about 100,000 times. That makes it much easier. This is an image of a star Beta Pictoris seen in the southern hemisphere, and it has around it a disk, a debris disk of the remnants of star formation and planet formation that, from an artist's point of view, we think looks something like this, where there's massive planets and lots of leftovers orbiting it. And we think with the GMT we'll be able to actually break up this disk and see the individual planets, and we'll be able to see it on scales that are comparable to the orbit of the Earth rather than the orbit of Jupiter. So working in the infrared makes this a lot easier, and we should have the capability to see Earth-like planets in close, Jupiter planets further out, and planets when they're young. This is the state of the art as it is today, though, for imaging Jupiter-mass planets. This is an observation of a bright star, which is, again, Beta Pictoris. Here's the star where we've suppressed and blocked out the light from the star, and this little blip, that little white spot, that's a planet with a mass of about 10 times that of Jupiter. So that's a giant planet, very big planet. That's the state of the art of detection. This is what we'll do with the GMT. We'll suppress the light from the star by about a factor of 10 million. Then a 10 Jupiter mass planet would stick out easily, 2 Jupiter mass, 1 Jupiter mass, and maybe you can see a half a Jupiter mass. This is a wavelength about 3.5 microns where the stars radiate from themselves. The point being that we'll go from this kind of bare detection to actually seeing the full planetary systems in the infrared by having this increased angular resolution and sensitivity. Now, the key to all of this is to defeat the turbulence introduced by the Earth's atmosphere. We'll talk a bit about how that works in a moment, but let me just show you some examples. This is a simulation of a star cluster, say a globular cluster around a nearby galaxy in exquisite conditions from the ground. So you go to the best site, say Mount Wilson on a summer night where the images are really sharp. This is a simulation of just a few arc seconds. You can see the stars are kind of blurred together. There's about 10,000 or 100,000 stars in this simulation. This is what the same area of the sky looks like with the Hubble Space Telescope. So you can see lots of the stars that were blurred together are now shown as individual stars, and this is the Hubble in the infrared. If we then go to the $8 billion James Webb Space Telescope that will go up in 2018, this is what it looks like. That's a big gain over what we had before. And then with the GMT with its 25-meter aperture, with adaptive optics to correct the atmosphere, this is what we think we'll see. So we just go back and look at that again. We go from what the atmosphere gives us to what we get with space telescopes to what we get with adaptive optics and a 25-meter aperture. You can see it's a pretty dramatic difference. And that's the key, whether it's looking at planets, stars, galaxies, is to achieve that high angular resolution. Just another example, this is a simulation of two galaxies that have just collided with each other. This galaxy passed through the disk of this galaxy and has set up a disturbance in there, a dynamical wave that turns it from an ordinary spiral into what we call a ring galaxy. If you're not familiar with this, you can have two galaxies that collide with each other, pass through each other, and not a single star ever collides. They just pass through the night, but they set up a gravitational disturbance that turns one of them into a ring galaxy. Now, if you look at that through the Earth's atmosphere, well, this is what it looks like. Not so impressive. Then you use adaptive optics in a 25-meter aperture, you can actually then recover the structure. You can then see these galaxies at distances of about 8 billion light years and resolve their internal structure. One of the things we really want to do is to measure the masses of black holes anywhere in the universe. As you might be aware, all big galaxies, including the Milky Way, we believe, harbor extinct massive black holes in their centers. The black hole in the center of the Milky Way is about 1 million times the mass of the Sun, and it's relatively lightweight. We now know of galaxies that have central black holes with masses of 1 billion times that of the Sun. The way we deduce their existence and measure their masses is we can measure the orbit of material in very close to the black hole, just in the same way that early astronomers measured the mass of the Sun by timing the orbits of Mercury, Venus, the Earth, Mars, and so on. By measuring this velocity as a function of distance, you can deduce the mass interior to that. The problem is if we look at a galaxy that's, say, 1 billion light years away, or even not that far, blurring from the Earth's atmosphere means that instead of seeing the nucleus, we simply, in a single resolution element, see the center of the galaxy and lots of stars, and the disturbance from the black hole is blurred out. So if we plotted up, say, the rotation of material around the black hole where it's centered here, the velocities are pretty minor, pretty small. If we could zoom in close to the black hole with adaptive optics, then we can see the stuff moving really fast, and then we can measure the masses of the black hole directly. The idea then is to look out when the universe was young. The black holes might have been smaller, although the ones we see out there actually look pretty massive, and watch their mass grow with cosmic time as they swallow stars whole, or perhaps as individual black holes merge with each other, and the black holes may grow in sort of multiples of 2 via merging rather than by swallowing stars. We don't quite know. We really want to measure the masses and look at the demographics. This is the famous image of the deepest image of the universe. You probably have seen this before. This is the Hubble Ultra Deep Field. It was taken with about 200 hours of exposure with the Hubble Space Telescope, from wavelengths from the visible out through the infrared. It shows galaxies when the universe was anywhere from about 5 to 11 billion years old. Some of these are relatively close, others are very, very far away. We have faked this a little bit in the sense that we've added, for simulation purposes, one galaxy to the center, which is this one. This is probably something you may have seen yourself. This is the Whirlpool M51. But simulated to how it would look at a redshift of 2 when the universe is about half its current age as seen by Hubble. So this is what the famous Whirlpool galaxy would look like if it were 8 billion light years away as seen with the Hubble Space Telescope. This is what it would look like with the 25-meter giant Magellan telescope. You can see now all kinds of structure that you can see that's not visible with Hubble. So we'll have the sensitivity to see galaxies way out when the universe was young, with the angular resolution comparable to what we can do today to see how did the spiral structure form, what were the giant star forming regions like, what was the balance between elliptical, spirals, irregulars, and so on. Lastly then, if we want to talk about individual discrete phenomena, if we look almost all the way back to the beginning and ask when did the first stars, the first galaxies form, and what were they like, it's a pretty interesting story. Theorists tell us that the first stars that formed were quite unlike the sun. They didn't have any of the heavy elements, carbon, nitrogen, oxygen, that's so important in the energy balance of the sun. They were pure hydrogen and helium. Their masses were about 1,000 times that of the sun. And as you know, the more massive a star is, the shorter it lives. And these first stars only lived about 1,000 years. And then they blew up. And they blew up with such an amount of energy that the first star to form in a galaxy was also the last, because when it blew up, it blew out all the gas so no other stars could form. This happened very quickly, produced heavy elements. Those heavy elements get distributed throughout the nearby volume. So this is a simulation of a galaxy when the universe was about 100 million years old. Here it is exploding, distributing all the enriched elements. Then the next generations of stars form, and so on and so on. And so fairly quickly you form galaxies that have amounts of heavy elements that are about 1% of what we have in the Milky Way today. Now, our best observations to date have reached galaxies at redshifts of around 7. That's as the light has been redshifted by a factor of 8, 1 plus the redshift. And this, again, is an observation with the Hubble Space Telescope. This is the galaxy that we think is out there. But the point is, this is an extremely difficult observation. And even with the Hubble, the rate at which the photons come in for this object after they've traveled 11 billion years is about 1 every 15 minutes. So you can imagine you're sitting there observing and you're waiting. One photon comes in, then you go out and you have coffee and check your email and walk the dog maybe, and you come back and maybe one more photon has come. It's a slow way to observe. So with a GMT, by having so much more collecting area, the photons will come in at about 17 per minute, which is pretty good. But there's a lot of sky that we have to deal with, so there's some interesting technical challenges. But building the big light bucket, the big collecting area, is part of the key to seeing out to these very early times. Lastly then, rather than looking at individual objects, if we look at the universe as a whole and ask what is it made of, this is one of the big surprises of modern astronomy and cosmology. Is when I was a student, we were just getting used to the idea that most of the stuff in the universe is dark matter, and that ordinary atoms and elements and nuclei are only about 20% of the total. But we now know that the elements and the particles that make up us and the Earth are about 4%. The dark matter is 20%, and the remaining 74% is this mysterious dark energy, the thing that drives the accelerating expansion of the universe. So we'd like to be able to measure the history of the expansion of the universe, understand what's driving it, and what is the nature of this mysterious dark matter. Is it Einstein's cosmological constant? Is it some fundamental new form of physics that we don't understand? We don't know. This discovery is so new, nobody really has quite a good idea of what it's about. And just to take a knock at theorists, the best theory misses the observations by only about a factor of 10 to the 100th power. So they've got a little work to do. So let's talk a bit then about the technology, how you actually make this work. How do you make a telescope so enormous that you can see back to the beginning of the universe, look at planets around nearby stars, and so on? Well, we're all familiar with refracting telescopes, and if you've ever tried to build one or use one, you know it gets pretty impractical if you want to make a big telescope. I love this little illustration of a European telescope where they tried to make a lens with all the stops and all the mounting to have a really high power telescope, and it gets pretty impractical. It's because lenses have to be transparent. You have to support them by the edge, not by the center, so they tend to absorb light and deflect under their own gravity, and it gets to be very difficult. The biggest refractors on the planet were built around the turn of the 18th, 19th centuries, so around 1860 to 1890. This, of course, is the famous Yerkes 40-inch refractor. The second largest is at Lick up there outside San Jose. So here's a nice picture of Einstein and various people at the Lick refractor in 1920, but by that time there were already reflectors larger than this, the 60-inch and soon the 100-inch at Mount Wilson. So refractors are kind of a dead end if you want to get to big telescopes. We learned fairly early on that it has to be reflectors. This just shows a gallery of interesting telescopes around the turn of the century from institutions involved in our project, but a lot of the famous discoveries in astronomy, like the nature of stellar chemistry, the nature of binary stars, the external nebulae, the scale of the Milky Way, and of course ultimately the expansion of the universe came from these individual telescopes, some of them here in Southern California or in the Southwest. So our idea is to build this giant telescope that will be about 20 stories tall. It will have 362 square meters of collecting area. An interesting fact, the part of the telescope that moves weighs 1,200 metric tons. If you've ever been down to see the 200-inch at Palomar, you might have heard that its moving mass is about 700 metric tons. But it has a collecting area only 1/20th the size of our telescope. So while we've increased the collecting area by a factor of 20, we've only less than doubled the mass, in fact. So it's about a factor of 20 gain in overall mechanical efficiency. The telescope is very stiff, and as you all know, if you go out and set your telescope up on a nice dark night, and every time you look into it, it shakes and bounces around, that's no good. You can't get good images if your telescope is shaking, and so we designed the telescope to be mechanically extremely rigid, and so the frequency which it oscillates is around 10 hertz, and it has very little amplitude, so it produces sharp images. The telescope, while very massive, in order to operate smoothly and not have vibration, has to float on a bearing made out of oil. So when the telescope is in operation, the entire 1,200 tons is floating on a thin film of oil, and so the telescope isn't actually touching the ground, it's isolated. The primary mirrors, which weigh about 17 tons each, they float on cushion of air, so they're not touching the telescope. And then the secondary mirrors, which are up there, not quite 20 stories, but about 15 stories up. In order to do the adaptive optics, we have the secondary mirrors not touching the telescope at all. They're simply held in place by a magnetism. So a magnetic field holds these thin secondary mirrors, and they vibrate just enough to take out the Earth's atmosphere. So while we build this massive structure, when we're actually using it, very little of it is actually touching each other, and it's all moving with very carefully choreographed balance to produce exceptional images. Now, the mirrors are an interesting challenge, making them and maintaining them. The first reflecting telescopes were made not of glass but of metal, something called speculum metal, which is a combination of tin and lead. And they had the advantage of you could polish them relatively easily, but they had the disadvantage they would tarnish. So imagine if to go observing every night you had to polish your mirror all afternoon before going out and observing all night. But that's what it was like for the early pioneers like Herschel. So this is a picture of John Herschel polishing his mirror. That's his wife, Caroline. I think she's holding a cup of polish rather than a cup of tea, but I'm not sure. But I think that's polish helping him. Sister, excuse me. Thank you. Yeah, that's a bad slip there. Yes, that was his. I've been to his house in Bath. It's an interesting place. You can see some of the last mirrors he made down in his basement there in England. But pretty tough duty to actually have to polish your mirror every night. This is the fabrication or the pouring of the first, what I call the GMT mirror, the Great Melbourne Telescope. I do this for our friends in Australia. But this was the last of the big speculum mirrors, where it was a 40-inch mirror made out of metal, poured into a mold that then gave it its approximate diameter, and then it was polished. These guys who look like they're dressed for a KKK rally, I guess you wear those hoods to protect yourself from the flaming metal. It must have been pretty hard. Now, the big advance was to make metal on glass mirrors. Glass maintains its shape. It's relatively easy to work with. It's much more stable than using metal, and you can put metal films on them that don't tarnish. But it gets pretty hard to make large glass mirrors. This is a picture of the fabrication of the Palomar 200-inch mirror, in which they melt the glass in a big furnace, and then they put it in a ladle, and these guys dressed up in all these flame-protecting gear then took the glass over and poured it into the mold. And if you've read the story of the 200-inch, remember the first one they made didn't work because as they were pouring in the glass, the mold came apart and the mold forms just floated up to the top of the glass, and it was ruined. Start over. You lose a year there. So the breakthrough was the group in Arizona recognized you couldn't make a mirror bigger than Palomar simply by ladling glass into the mold. It's just not possible. Some of the glass is already cooled while you're pouring in the rest of it. And nobody wants to handle these giant ladles full of flaming hot glass. So the innovation was to make a mold and then put the glass inside the mold. So let's talk a bit about scale. This is the Palomar 200-inch looking at the back side. This is the first of the GMT mirrors also looking at the back. but you can see the difference in scale. In fact, let's put them side by side, and now you can see how much bigger a GMT mirror is compared to a Palomar. And it's just not practical to ladle that much glass. So as I said, we build the mold and then put the glass on top of it, and I'll just show you a few slides of how this works. This is the furnace underneath the football stadium at the University of Arizona, where the furnace materials, the fire brick, the stuff that will hold all the molten glass is being laid down. They then build inside this furnace a mold that is going to be mostly empty space by the time it's done. So there's this material that will prevent the glass from filling all the space, yet not burn up. It's like the heat tiles on the space shuttle. It's a very similar material, and then we'll remove it once the glass is actually cooled. So there's a period of about a year which they build up the mold, put it all together very precisely. Then they inspect individually about 20 tons of glass that comes from Japan. The glass starts as sand in Florida. It's then shipped to Japan, where it's combined with some borax and then melted and treated individual small pots, broken up, sent back to Arizona, put in the mold. The 20 tons is then loaded into the mold, one piece at a time. You can see this little video where they're loading in then the glass chunks on top of the mold materials. Each piece weighs about 5 or 10 pounds, and it takes a few days to fully load the 20 tons of glass into the mold. Then, once all the glass is in, they bring the top of the oven over. In this case, there's heating coils that look right down onto the glass in the mold, and they will simply melt the glass in place, so it flows into the mold and takes the shape of the mirror. Now, the problem is if you just melted the glass, by the time you're done, you have to grind a curve into the mirror, and it's a big curve. So the trick is they put this in here, and then they rotate the oven while the glass is liquid. Just like if you put water in a bucket and you spin it, some of it rises up on the edge, and you wind up with a naturally curved shape. It's not an optical shape, but it gets you a long way towards where you want to be and saves a whole lot of polishing. So we'll show you a little more of the details here. Let's go on from this movie. Come on. That wasn't a good, okay. This is a video from inside the oven when we made the third mirror just the week before last, about 10 days ago. So you're looking at 10 tons of glass chunks as they melt over a period of about 6 hours. So it goes from the chunks, they kind of get soft, they flow together. Now you can see through them to see the mold. They let it cook for a while so all the bubbles float away, and then it's done, and it's now a piece of glass with the mold still inside it. If we look over, we put some marks on the edge of the furnace so we can see just what the glass level looks like, kind of like the marks on the side of a swimming pool. You see the glass melting. It flows down then into the mold, and you can see then when it stops, that's a good sign. That means the glass is wound up in the right place. So it's quite an experience to see this giant furnace spinning full of red-hot glass. And knowing that if something went wrong, you wouldn't last very long, as the whole room filled with 20 tons of molten glass. So the mold is inside the furnace, and the whole thing actually rotates. Yeah, about 4.5 for our mirrors. For the fastest mirrors, the smaller mirrors, they go as fast as 9 RPM, and at 9 RPM, that thing is really moving. I've seen ones at 6, at 9. Ours is 4.5, and so it's kind of sedate. Let's see here. Well, can we get back to where this spins? And the high-speed rotation goes on for about a week, and then they slow it down while the mirror is cooling, and then it spins at a slow speed for about 4 months. So the whole thing sits on a giant bearing, on a giant turntable. There's megawatt, almost of power going into this thing while it is spinning. It's pretty interesting. They do it at night when they can take basically all the power from Tucson to fire this thing up and have it go around. So it's yeah, the peak temperature is usually set to happen around 1 a.m. so that nobody notices. So it cools then for about 4 months, and 4 months seems like a long time, but the Palomar mirror cooled for almost a year, right? And if you had done this mirror the same way as Palomar, it would take about 2.5 years to anneal, and that's too long. So after 4 months, they take off the top, and you can see, okay, it looks like we've got a pretty good mirror. Strip off all the material. Now you can see the mirror and a person up here for scale, just to give you an idea of how big the blank actually is. But it still has in it all of the mold materials. They then lift it off the floor of the furnace by attaching a steel frame onto it, and the steel frame is glued on with bathroom caulk. Literally Dow Corning bathroom caulk. They put some suction cups on there, glue it all up, let it cure for a few weeks, and then they lift 40 tons. So it's 20 tons of glass and 20 tons of mold material, turn it on its side, and then they spend about 4 months removing all of this stuff from the back of the mirror before you wind up with just the glass. And then it's lightweighted by about 85%. So 85% of the mirror is empty space. This is what it looks like when the back side is done, all polished, ready to be turned over. Then they put it on the polishing lap. And this is a pretty interesting high-tech bit of hardware. This is a polishing head that changes shape as it flies across the surface of the mirror to take out that extreme curvature. So it's moving around and it's constantly sort of stressing and bending itself to get just the right curvature. Because these mirrors, being off axis, they have a shape that's kind of like a potato chip. It's kind of like a laser, not like a, what do you call those things? A Pringles potato chip. And it's 14 millimeters higher on one edge than it is on the other. Well, 14 millimeters doesn't sound like a lot, but that's 40,000 wavelengths of light, and we have to polish that to an accuracy of 1/20th of a wave. So it's a pretty challenging thing to do, and you all know there's no point in building a big telescope if the mirror's no good. You'll make crummy images. So this is the genius behind the Mirror Lab. When he says it's done, then we say, okay, it's ready to go. So let's talk a bit then about adaptive optics. As I said, the problem with big telescopes, and you've probably seen this with your own telescopes, is you're looking through a turbulent atmosphere that's distorting the wavefront that's traveled sometimes billions of years. And what we do is we try to cancel out those distortions in a way that's pretty much like what you do with your noise canceling headphones. That is, we measure what the distortions are from the atmosphere. We then have a mirror that changes its shape about 1,000 times a second in exactly the opposite shape of the atmospheric distortions, cancel them out, and then we get images that are essentially the same as the atmosphere. So this is a highly magnified version of a star. As you see it through the atmosphere, it's bouncing around all over the place. It's expanding, contracting. There's all these little knots that we call speckles. With an adaptive optics system, the first thing we do is we stabilize the image wander. So once the AO is turned on, you'll see the star no longer wanders around. Then we can try to correct the high order modes, all the little lenses in the atmosphere, and concentrate the light back into its theoretical maximum of what the optics can allow, which will happen any second now. There. So that's the difference then with the adaptive optics on as opposed to what we saw with it off. That's when you get to your theoretical resolution like the Hubble Space Telescope, when you turn on this rapid correction that takes out all the distortions caused by the atmosphere. And it doesn't concentrate all of the light. There's a little bit around the outside that we can't do, but you get most of it. And then once you turn the AO off, looks like junk again. So let's see here. So the way we do this is with a mirror that I say it's kind of like a loudspeaker. It's got attached to it a sheet that's only about 2 millimeters thin of glass, about 1 meter across, and glued to that are thousands of magnets, actually hundreds of individual magnets. Let's see, we can come back to this. These are the magnets, and they push and pull on the mirror, changing its shape to either advance or delay the arrival of the light to take out all the distortions caused by the atmosphere. It's a pretty impressive and complicated piece of machinery. It's all attached to a very high precision, ultra lightweight optical reference surface that tells us where the glass is at any time. You know, as we move it 500 to 1,000 times a second. And that then allows us to take out the atmosphere. So just show you an example here of what has happened with adaptive optics in the past 10 years. These are 3 images of a star in Orion, actually in the trapezium. It's Theta Orion B. If you're familiar with Theta Ori, it's one of the stars in the trapezium. Turns out it's a double star. Turns out it's actually more. But this is what it looked like with state-of-the-art adaptive optics in the year 2000. This is what we could do in 2003. This is what we can do now, where this star is now a double. There's another star showed up here. And all these rings around the stars, that shows you that you're reaching the actual theoretical maximum resolution. That ringing is the imprint of the circular aperture of your telescope as it interferes with the wavelengths across the aperture. So we're now able to concentrate 98% of the light into a perfect diffraction limited image and see the detail that's theoretically possible with the telescope and not limited by the atmosphere. So this is just kind of a fun picture. This is that 2 millimeter thin shell inside a vacuum tank where we coat the aluminum on it, and it's a pretty delicate operation because you've got a piece of glass this big, 2 millimeters thin, extremely fragile, but it costs $2 million. You don't want to drop it. It's been done. Wouldn't want to. Uh, no, don't ask, don't tell on that. Now, in order to make the adaptive optics work, you need a bright star that gives you a reference to allow you to measure the distortions from the atmosphere. Well, as you know, there are not bright stars everywhere because you can only correct in pretty close to the star. So what we do is we make our own stars. That is, we take high-powered lasers that are tuned to a particular resonance from ionized sodium, launch them up from the telescope. They then see ionized sodium atoms about 90 kilometers up in what they call the mesosphere, the very top layer of the atmosphere. And those sodium atoms, it turns out, come from very small meteorites, particularly from the Perseid shower. And they're just floating up there, and then they scatter back and reflect some of that sodium to us, and they make an artificial star. So that anywhere in the sky, we can make a bright star. And typically what we do is we make 6 bright stars in a little circle, a little asterism, that then give us all of the information about the turbulence in the atmosphere that allows us then to correct the distortion and get back to that original perfect optical performance. So this is a sodium laser from a telescope in the north of Chile. You can see the beautiful Milky Way. Turns out that when you're the first people to do this, it's very hard and very expensive. This thing here that looks like a large building on the side of the Gemini telescope, that's the laser. So it's it's a pretty good sized room with all kinds of gear to make a 20-watt laser. You can now buy a 20-watt laser that you could carry on the plane. I don't think they'd let you carry it on the plane, but it's that kind of size and the cost has come down. So we anticipate having 6 20-watt lasers attached to the side of the telescope that will allow us to look anywhere in the sky. But you do have to be careful. You don't want to shine that 20-watt laser at an airplane. That's not good for them. You don't want to shine it at a satellite, particularly a Russian satellite, or Chinese satellites. They're up there now. But you can't even shine it at a U.S. satellite, so we have to have permission from the airport authorities and from U.S. Space Command before you can actually shine the laser anywhere. So it's a complicated business of getting all the clearance. And if Space Command calls you up and say, turn off the laser, you turn off the laser, or else. Gemini once was, I think, 10 seconds late in turning off their laser, and they couldn't use it for 6 months. The government was not happy with them. So this is an example then of what that can do. This is a simulation of an image of a globular cluster around the nearby elliptical galaxy Centaurus A, as it would look with the Hubble Space Telescope, and that's really what they look like. You can't see the individual stars, with adaptive optics on current telescopes and with adaptive optics on the GMT. So if we zoom in and compare, say, current 8-meter telescopes with a GMT, you see the dramatic difference. Many of the stars that are blurred together are now resolved here, simply because you're concentrating the light a factor of 3, both in X and in Y, and so you've resolved out all the blurred stars together and made this enormously powerful tool for looking at dense stellar regions, black holes, galaxies, what have you. The top end of the telescope is almost as complicated as the bottom end. We have all these secondary mirrors, and they're all sort of moving around and adjusting their shape and their figure. It's a very complicated piece of equipment, but we're pretty confident we'll make it all work. So then to wrap it up, let's talk a bit about where we're going to put all of this, the site, and what the dome looks like. This is a wonderful sketch from Russell Porter of the 200-inch dome in the 1930s. Things have evolved a bit since then. We're going to put our telescope in Chile at the southern end of the Great Atacama Desert. Now, this is a place that is so dry that there has been no recorded precipitation in 40 years in some place. Now, our spot, we do get some snow about every other year. We'll get a little snow in July, but it never actually rains. You just get a little high humidity occasionally in January and snow in July, and it is really, really dry. The elevation's about 8,500 feet, so it's a workable environment. It's not super high, but it's high enough that you're above most of the muck in the atmosphere, and it's a really very nice place. And as you'll see, there's really no light pollution, but there's now several observatories in Chile. So here's Santiago, where you fly into La Serena, the seaside town, and then we drive up here about 3 hours to the north. But if you look at sort of the development of observatories around the world today, there's really only 2 places that people are talking about big telescopes: Hawaii and Chile. So we put ours in Chile. We think it's actually a slightly better location. So this is what it looks like. This is where our current telescopes are at Las Campanas. This is where the GMT will go. You can see it's a pretty dry place. There's not much that grows there. And since there's no water, there's no people, that means there's no lights. And it's extremely dry. And you can see if you get lost, like this fellow did, it's there's not much out there to eat or drink. But it's really an exceptionally good place. And fortunately, one of our partners, the Carnegie Institution that built Mount Wilson, they own this land. They bought it in the 60s for virtually nothing. The area that they own is equivalent to the size of Los Angeles. And they bought it for, I don't know, $10 or something a long time ago. It's basically nothing but goat pasture, but they put in the roads and the wells and the power system and all, so it's really ready to go. Yeah, if you drill deep enough. The nice thing about being in the foothill of the Andes is the snow melt comes down and it flows downhill, and once you drill deep enough, it's a steady supply of water. Pretty nice. So this is what the mountaintop looked like while we were doing the testing to measure the atmospheric turbulence, the weather patterns, and so on and so on. This is a little tower where there's a small telescope. I think it's a Meade 8-inch, two of them, to measure twinkling of the stars. And here's the person driving up at night to open up this little dome. Then once we cleared the top of the mountain, this is what it looks like now. It actually looks a little flatter than this, but we took off 90,000 cubic feet of rock, which is a lot. We lowered the top of the mountain by about 27 feet. We cleared an area equivalent to 4 football fields. But we're going to fill it up with a big telescope and all the stuff that needs to go with it. So this is what the site will look like when we are done in 2020-ish. We will have the world's biggest telescope, a 22-story building protecting it, all the infrastructure we need to actually do astronomy, and on a place where basically it never rains. It's occasionally cloudy, but not very often. And the only light pollution we ever see really is a few trucks going along the Pan American Highway. So it's a wonderful place. The center of the Milky Way galaxy goes right overhead. You can see all the beautiful stuff in Sagittarius and Scorpio. Just rather than looking down through the muck, it's straight up there. You see the Magellanic Clouds, which are really pretty impressive, and all of the southern Milky Way. So we think it's a pretty special place. We think it's going to be a fun project. It's going to be another 10 years, realistically, 8 to 10 years before it's going. But this is what it would look like, modulo the clouds that the artists like, where we've got our laser beams, 2 lasers per beam, looking out the sky just as the sun goes down to look back, perhaps, to the first stars, the first galaxies, or maybe even Earth-like planets around, say, Alpha Centauri. So thanks so much for your time, and I'd be happy to answer any questions or chat.